8-2. Vectors in the coordinate plane. So we're going to look at the vectors in a coordinate plane, just like the title said. There you go. So the first we're going to look at is the component form of a vector. Remember in 8-1, toward the end there, we talked about the component form where we broke up the vector into the x and y value, the horizontal and the vertical shift there. And so the component form is going to look like this. Notice how I have this special parentheses here. x2 minus x1, comma, y2 minus y1. And this is how we're going to write the vectors here. You'll see it a little more clearly as we move on. So here's vector AB. And we're going to draw vector AB. So here's A, B, head, tail, and then we've got the horizontal and the vertical components. So if A is x1, y1, and B is x2, y2, then this component is y2 minus y1, and this component is x2 minus x1. The distance here, from here to here, is x2 minus x1, and the distance from here to here is y2 minus y1. Alright, so let's do some examples here, see if we can figure out what we're talking about. Express a vector in component form. Okay, so we've got AB, vector AB, which is, the points here, A is -4, 2, and B is 3, -5. So we're just going to express this in component form. Let me show you how we do this. AB. The first thing I do is I label my points. Sounds familiar, hopefully. x1, y1, x2, y2. And so I say my component form I've already written down. x2 minus x1, y2 minus y1. So let's just plug in these values here. So x2 is 3 minus x1, which is -4, y2, which is -5, minus y1, which is 2. So 3 minus -4, that'll end up being 3 plus 4, which is 7. -5 minus 2 is -7. And that is your answer. Hopefully you're looking at that and saying, oh my goodness, that is very, very easy. So I'm going to give you 2 U-tries right off the bat. So A is -2, -7. B is 6, 1, and then the other u try, A, 0, 8, B, -3, -9. So at this point, I'd like you to pause the video and we'll come back and look at this. Okay, here we go. So I'll work through this first one and then I'm just going to give you the answer to the second one. So the first one I'm going to make sure I label, and then I say vector AB equals x2, which is 6, minus x1, and y2 minus y1. And so I end up with 6 minus -2, which is 8, 1 minus -7, which is also 8. And there's your answer for that one. For this one here, you should have gotten -9, -11. Boom. All right, magnitude of a vector. And we find the magnitude of the vector, so remember that's the length of the vector. So in order to find the length of a vector, you might need the distance formula. It's all coming back, right? Okay, distance formula. Mr. V said years ago, you're going to need to remember this. And you said, no, I'm not. Well, here we are. So the absolute value of your vector, or the magnitude of your vector, right, equals x squared minus x1, x2 minus x1 squared plus y2 minus y1 squared. So that's the distance formula. Think about why this needs to be absolute value here as I start this example. This needs to be positive. We use the absolute value to say this needs to be positive because a distance cannot be negative. A distance or a magnitude here needs to be positive. All right, so here's your example. A is -4, 2, and B is 3, -5. So we just need to plug in these values to find our magnitude or our distance. So I'm going to plug in, I'm going to label first to help me keep track of stuff, x1, y1, x2, y2. So my absolute value of my vector is going to be the square root of x2, which is 3, minus -4 squared, plus y2, which is -5, minus 2 squared. Now I'll resolve this stuff here. So 3 minus a -4 is 7. 7 squared is 49. Square root of 49 plus, this is -7 squared. So that's also 49. So I've got the square root of 49 plus 49, which is 98. And the square root of 98 is approximately 9.9. So that is your magnitude. So I'm going to give you guys a U try. Distance formula should be somewhat familiar. Just find the magnitude of vector AB, where A is 0, 8, and B is -9, -3, round to the nearest tenth. Alright, so label these guys, go through the formula, and then do the square root at the end. Pause now and do the U-try. Alright, you should have gotten 14.2. And that's that. Next section here, we are going to look at vector operations. So we're going to write a little bit here, and before we start doing any examples. So if vector A equals A1, comma A2, and vector B equals B1, comma B2, K is scalar. So if this stuff is true here, then we are going to see what we can do with our operations. So here is vector addition. So if I'm going to add these two vectors together, vector A plus vector B equals A1 plus B1, comma A2 plus B2. So you just add you add the x values and you add the y values for vector addition. Let's look at vector subtraction. I'm assuming it's going to look very similar, right? So if I have vector A minus vector B, then I get vector A1 minus B1, so those are the x values here, A1 and B1, comma A2 minus B2, so A2 minus B2, just very similar to the addition, right? Okay, next is, and the last operation that we're going to look at here is vector scalar multiplication. So I've got k, that's my scalar, times my vector A equals k times A1, comma k times A2. Okay, so we are going to do some of these here, and hopefully this will make sense. Example time. So we're going to do some operations. Oops. Yeah. Where vector W is -4, 1. Vector Y is 2, 8. And vector Z is -3, 0. Alright, so here's our first example. Y, vector W plus vector Y. So I'm just going to write out what those vectors are first. So I've got -4 and 1, which is my W, plus vector Y, which is 2, 8. So those, I'm adding those together. So I'm just going to add the x values and add the y values. So -4 plus 2, -4 plus 2, and 1 plus 8. -4 and 2 is -2. 1 and 8 is 9. And there we have our example. Oh, if you're following along in the notes, this was a 5 on my notes, but I'm going to leave it at 8 because here we are. Okay. Phew. Alright, so there's vector addition. You go ahead and try now no, let's do this one together actually, a we try. I've got vector z minus 2 times vector y. So let's see how this works. So we try doesn't work super well as a we try here, but let's see. Z is -3, 0 minus 2 times y, vector y, which is 2, 8. Now think about this -2 here and think of it as I'm going to multiply this -2 times each of these here. You're going to distribute it like you would distribute a -2 in any other kind of circumstance with parentheses here. So it would be like plus a -2. So let's just do this. We're going to start here. I am going to rewrite this -3, 0 and then do this computation here and then do the rest of the problem here. So -2 times 2 is going to get me, so I'm going to put a plus here because I'm distributing this negative into both of these sections here. So -2 times 2 is going to get me -4. -2 times 8 is going to get me -16. Now I'm going to add these. So I'm going to add these two and these two. -3, -4, -3 plus a -4, and 0 plus a -16. So that'll get me -7, -16. That's it. Alright, let's go ahead and you guys do one without me. 4 times w plus z, vector w and vector z. So go ahead and write those out and follow these examples. Pause the video now. Okay. Instead of just giving you the answer here, I'll work this out, and if you can fast forward, right, if you need to. So I'm going to say 4 times w, which is -4, 1, plus z, which is -3, 0. Alright, so this 4 gets distributed. So I've got -16, 4, plus -3, 0. Now I add these together, and I add these together, and so I get, -16 plus -3 is going to get me a -19. 4 plus 0 is 4, and I have my answer there. My vector, when I add these guys together, is -19, 4. Alright, let's keep moving. Unit vectors. Magnitude of 1 unit. What does that mean? Let's find out. of 1 unit. Unit vectors have a magnitude of 1 unit. So we're going to say vector u equals vector v over the absolute value of vector v, or 1 over the absolute value of vector v times vector v. Right, this expression here and this expression here, these are equivalent, right? This fraction is the same as this fraction. You're multiplying this, so this would end up here in the numerator anyways. So let's see what we are talking about here. How can we use this? So find unit vector u find unit vector u with same direction as vector v, which equals -2, 3. All right, so let's see if we can figure this out. Our formula up here, vector u equals 1 over the absolute value of vector v times vector v. So let's plug in our information here. 1 over -2, 3, which is our vector v, the absolute value of that, times -2, 3. Okay, now what do we do? So now what we need to do is we write, okay, 1 over, what are we going to do with this stuff here? Now let's, this is the time when I give you a whole nother formula that you are going to love quite a bit. I look at this, and I need to use this new formula that I have here. The absolute value of this vector equals the square root of a squared plus b squared. So here is a formula that you want to know. So let's do it. So if this is a and this is b, like here, then we have the square root of a squared plus b squared. So I say the square root of -2 squared plus 3 squared times -2, 3. Notice how what I've done here with this formula is I've taken away the vector sign, right? So now I can manipulate this in a different way because I don't have a vector anymore in this denominator. So this equals 1 over, so let's see, what would this be? -2 squared is 4, plus 3 squared, which is 9. 4 plus 9 is 13, so I've got 1 over the square root of 13 times -2, 3, times my vector -2, 3. And I learned previously that I can take this scalar and multiply it by each of these components of my vector. So this is going to be 1 over 13 times -2, which is -2 over 13, and 1 over square root of 13, oops, sorry, square root of 13, gosh, -2 over the square root of 13. 1 over the square root of 13 times 3 is 3 over the square root of 13. Now we have a problem. We don't want the radical in the denominator, so let's rationalize. We multiply each of these by the square root of 13 over the square root of 13, and we get our new scalar, our new vector, which is negative 2 times the square root of 13 over 13, and 3 times the square root of 13 over 13. And that is how we find the unit vector. Boom. Let's do another example of this, and then we just have a little bit more. We're good. We're done with this section. All right. You try. Find the unit vector. So here's my vector. Vector W is 6 and negative 2. So look at the notes that we just took, how to find a unit vector, copy that stuff down, and follow that example to find the unit vector. Pause. Okay. So I'll work through this since we just did that little one. So my formula here is 1 over the absolute value of 6, negative 2 equals 6, negative 2. And this is what I need to convert here. So 1 over the square root of 6 squared plus negative 2 squared times, I put equals up here, didn't I? Times my vector 6 minus and negative 2. Okay. 1 over 6 squared is 36, negative 2 squared is 4, 36 plus 4 is 40, so I have the square root of 40. Don't miss that square root sign there. That radical is easy to forget. Times 6, negative 2. Now, I'm going to rewrite this as 2 times the square root of 10, right? Because this is 2 times 2 times 10. So I've got 1 over 2 times the square root of 10. And I'm going to multiply that by 6, negative 2. So I'm going to go this way now. So that'll give me 6 times 2 over the square root of 10. 6 over 2 square root of 10. And negative 2 over 2 square root of 10. So let's rationalize the denominator, and let's also do some simplification here. So 6 divided by 2 is 3. 2 divided by 2 is 1, so I've got negative 1 over the square root of 10 and 3 over the square root of 10. So my new vector here, I need to rationalize this, multiply each of these by square root of 10 over square root of 10, and I have 3 square root of 10 over 10, and negative square root of 10 over 10. Put that in my vector notation. There it is. Alright, now we're going to do this last bit of this lesson. And it is, we're talking about standard unit vectors. So I've got this vector I, which is 1, 0. So this is a vector that just moves to the right one place. Doesn't go up and down, just moves to the right one. And J, which is a vector that doesn't move horizontally at all, but it moves up 1. So those are two standard unit vectors. Now, let's look at this linear combination. of I and j.